Okay, I understand that.
Okay, so welcome everyone to another season of the Seminar in Probability for Graduate Students. The goal of the seminar is that the students discover active research areas. So 1 week ago, one of our students gave the introduction of this paper, and now the speaker will talk about it.
Thank you.
Sorry, for today we are extremely excited to have Jeremy Bettinelli as the speaker. He's a French probabilist. He made his PhD in Orsay with Gregory Mermont, and then he went to Berkeley for a postdoc. Later, he returned to France, to Nancy, and now he works in École Polytechnique. He has really impressive mathematics and also very impressive visualizations of this mathematics. So I am really looking forward for this talk, and thank you for being here, Jeremy.
Thank you very much for this nice introduction. So today I'm going to talk about Brownian surfaces, and more especially about Brownian maps and Brownian disks. Brownian disk is an object that we introduced with Gregory Mermont, and which generalizes what we now call the Brownian sphere, but maybe you've heard the word Brownian map before, and that's the same thing. Okay, so let's start. The objects I'm going to consider are what we call plane maps. So what is a plane map? A plane map is a graph. So a graph is a set of vertices, the black dots here on the picture, and edges. The edges link the vertices. And this graph is embedded on a surface. So it can be the sphere here, or the plane. That's exactly the same if you consider that one of the faces is the unbounded part of the plane. And you also want the graph to be connected, which means in one piece. And also notice that you can have, I don't know, do you see my arrow? Or?
Yes,
yes,
we can see it.
You see it, okay. So you are allowed to have multiple edges like this. So here you have 3 times the same edge. This is allowed. And you also allow what we call loops, which are edges linking the same vertex twice. Sorry?
No, sorry, that was me having problems with the technology. So the YouTube started in my computer. I'm sorry.
Okay. And finally, what I call the face of the map is something like this. So it's an area delimited by the map, or more rigorously, a connected component of the complement of the set of edges. Right, so I'm going to give you an example explaining why it's called a map. I'm not sure you're gonna like it. Sorry about that. So this is a map, but I wanted it to be connected. So sorry, guys. This is only a part of the world, and you're not on it. Well, so this is a map, and it has to be connected, which means that I cannot have 2 parts. So I as I'm living here, I removed your part. Sorry about that. Okay, for a technical reason, we are going to consider rooted maps. A map is rooted if you distinguish with that little arrow here a corner of the map. So a corner is you take a vertex and you turn around the vertex. That's an area between 2 edges. So here, this is a corner here. And when you have a corner, you say that your map is rooted. And the corner here is called the root. Next, we'll also really consider maps up to small deformation, which means that here this map on the left is the same as this one, because you can go from this one to that one just by simply changing a bit the edges. So what I mean by that is that the exact way the edges are drawn on the surface does not matter. What matters is how they are arranged with respect to each other. But here, for instance, this map is not the same as that one. It's the same graph. But if you want to go from this map to this map, you need to put this little vertex inside. And when you do that, the edge, this edge has to cross this one. So I'm saying that it's not the same map. Another way to say it is that the number of corners in a face is called its degree. Here I have a triangle, which is a face of degree 3. Here also, and here I have a face of degree 2. I have only 2 corners, but in this map here I have a face of degree 4 because I have 1 corner here, 1 here to the right, 1 here to the left, and 1 here. So this here is what we call a quadrangle, a face of degree 4, whereas here it was a face of degree 2, so it's not the same map. When I have a map, so the point will be to have a given map, a random map, and to see how it behaves when the number of faces is large. So I have to explain how I see a map, and the point of view I'm going to use is the point of view of a metric space. So I'm saying that my map is a metric space. So it's simply a finite set of points, the vertices, and the distance between 2 points is given by the length of, by the number of edges you need to cross to go from one point to the other. So on this very simple example here, this point is at distance 2 from this point because you need to cross 2 edges, or to move along 2 edges to go from this vertex here to that. Of course, you can have many possibilities. Here you have 2 possibilities, but the length is 2, so the distance is 2. So when I take a random map, I have a random metric space, and I want to compare metric spaces, so I need a topology. The topology I'm going to use is the Gromov-Hausdorff topology. So that's something that was already introduced, but let me remind what it means. The Gromov-Hausdorff topology is a way to compare metric spaces that are not naturally embedded somewhere. So here I have, I'm in the plane. So I have these 2 sets here. Imagine that this is full, does not have any color, but so you have these 2 sets. And you want to say that they are, well, they look similar, but they are not embedded at the same spot. So the thing is, you put them both as best as you can on top of each other. And there, once you have done that, you use the Hausdorff distance. The Hausdorff distance is just the smallest amount by which I should enlarge one set to swallow the other set, and vice versa. So if I had this length d to the red set here, I will have a big thing like this that would be that will completely contain the green thing. And if I add this to the green thing, I will also completely contain the red thing. So that's the Gromov-Hausdorff topology. More rigorously, the Gromov-Hausdorff topology is defined like this. So you take x, d, and x prime, d prime, 2 metric spaces, considered up to isometry. So it means that if you have 2 metric spaces that are isometric to each other, you say that it's the same space. And you compare this, the distance between these 2 spaces is the infimum of the Hausdorff distance between phi of x and phi prime of x prime, where phi is an isometric embedding of x into a common metric space Z, and phi prime is an embedding of x prime into the same metric space Z. So this is actually a very big infimum because it's an infimum over all metric spaces Z and isometric embeddings of X and X prime into this. And then, so you embed X and X prime into the same metric space. You look at the Hausdorff distance between these two, and then you take the best embedding you can, giving the smallest distance. Right. So now I can give you the first result, which is due to Jean-François Le Gall and to Grégory Mirmont. It's really two different papers, the same result, the same year. Actually, it was just a couple of weeks apart on the archive, but it's not a joint work. It's two separate works. The theorem is the following one. So you take a random map Qn, which is a quadrangulation, meaning that all faces have degree 4. And the n here means that I have n faces. So among all the possibilities to make a quadrangulation with n faces, you take one uniformly at random. Okay, if you have n squares, there is only a finite numbers to glue them together to get the sphere. So this is actually a random variable taking values in a finite set. So there is no problem of taking a uniformly distributed one. Now you see this as a metric space. And you, instead of putting length 1 to each edge, now you put this factor, so roughly n to the -1/4, up to a constant that will, on which I will talk later. And once you do that, so you have a random metric space, then it converges toward a metric space, which is called the Brownian map or the Brownian sphere. If you want, you can say it like this: converging for the Gromov-Hausdorff topology, it means that you can embed all your spaces into the same metric space in an isometric way, in such a way that on this space you have convergence for Hausdorff. Okay, so you have your metric spaces. You can embed every of these metric space into a common metric space, let's say Z, and also the Brownian map into Z, in such a way that there you will have really convergence for the Hausdorff topology. Of course, if you have questions, don't hesitate to stop me and ask questions. So that's the results. Maybe the main result in this area, the first one. Right. I already said that. So this is a picture of a large plane quadrangulation with 50,000 faces. So if you look closely, you will see that every face has degree 4. And if you have a lot of time, you can count that you have actually 50,000 faces here. You also need a good eyesight. Well, this is embedded into 3D in such a way that the edges should have as much as possible the same length. Of course, it's not perfect. Some edges are a bit longer than other, but this is the best the software can do, and it gives you a nice idea of how the distances are on this random metric space. Well, when you see that, it looks kind of fractal. It is actually a fractal object, but nonetheless, we can show that this is topologically a sphere. So it means that it's homomorphic to the two sphere of R2 of R3. So let me give you a small history behind the results. First of all, in 2004, Chassin and Schaeffer showed that the scaling factor is n to the 1/4, which means that the distances in a random quadrangulation with n faces are of the order n to the 1/4. for instance, the diameter is n to the 1/4, which is actually very small. We could expect that it could be higher if you take the very naive idea that if you take n squares on the regular grid, you would expect that the length of the grid is of order root of n, but actually it's way smaller than that. It's n to the 1/4. Then Marker and Mokadem introduced the Brownian map. So they introduced the scaling limit, the space Brownian map, and they showed convergence in some sense for some functionals. And then Le Gall showed that the previous result holds, but up to extraction of a sequence. So he showed that if you take this sequence here, it is relatively compact, which means that you can extract subsequences along which you have convergence. So this sequence has accumulation points, but a priori you can have different accumulation points. And then in this paper, he showed that there is only one accumulation point. And this is actually why the title of the paper is Uniqueness of the Brownian map. So meaning that every accumulation point of this sequence is actually unique. It's the same. Then he also showed that the Hausdorff dimension of the Brownian map, or at the time of any subsequential limit, is 4, and that they all have the same topology. And he showed later with Paulin and Mirmont also showed the same result, that the topology is that of the two-sphere. And finally, in 2008, Boutier and Guiter studied the distance between three points. So if you take 3 points uniformly at random inside a random map, then you can study they found the joint distribution of the length between these 3 points. If you know the Brownian motion, you know that the Brownian motion is the scaling limit of a random walk, and which is really really nice about this this result is that if you take any random walk, provided it has steps that are nice enough, it will converge to the Brownian motion. And this is called a property of universality. Whatever the Brownian, whatever the random walk you consider, the scaling limit is always the same, up to a constant, which is the variance of the steps. And here you have the same kind of result for the Brownian map. Actually, if you take a well, not too degenerate sequence of maps, then it will always converge to the Brownian map. And we actually have at the day a lot of cases where we can show that we have convergence to the Brownian map. Let me point out that all these results use the result of Le Gall and Mirmont, that for the quadrangulation we have convergence. This is a very important step. And then Le Gall actually found a method to show that a class of maps converge also to the Brownian map. And this is way more simple than showing that the quadrangulation converge to the Brownian map. What I mean by that is that you need to know that at least one sequence of maps converge to the Brownian map in order to get the other classes of maps. I will not enter into the detail, but many maps, many classes of maps converge to the Brownian map. The only thing you have to do is to change the constant here before the Brownian map. Well, okay. So this is all for the Brownian map. Now let's talk about the Brownian disks. Earlier we had uniform quadrangulations on the sphere. So now I'm going to take another topology. I'm going to take the topology of the disk. So I take a quadrangulation with a boundary, or if you prefer, a quadrangulation that is drawn somehow on the disk. This is not exactly the case because here I just take a map with, let's say, n faces of degree 4 and one, exactly one, which I call the external face of arbitrary degree. If I do that, and I don't ask that the boundary is simple, which means that when I go around the boundary, maybe I will encounter the same vertex more than once. This is what I call a quadrangulation with the boundary. So once again, I have a map, a plane map, with faces of degree 4, except one, the one that contains the root. Right. So what can we say about a large random map with a boundary? First of all, let's start with the generic case. So now we have two parameters. I have the number of faces as before, but now I also have the length of the boundary. And well, it's quite clear that if the length of the boundary does not satisfy the right constraint, I can have different possibilities. So for instance, the easy case is when the length of the boundary is exactly 4. It means that I have a quadrangulation without a boundary, because the boundary is also a square. Then I know that this will converge to the Brownian map. So I need the boundary to be a bit longer than that in order to see something. And actually, the right regime is when ln is of order the square root of 2n. So if ln is equivalent to some positive finite number times the square root of 2n, then I have convergence towards a random metric space, which I call the Brownian disk of perimeter L. L being this L here. Let me just, sorry. So this is a result that I obtained with Gregory a couple of years ago. And as actually Legal did before, showing the convergence towards the Brownian map, he obtained results on the limit because he actually showed that the same sequence, but without for quadrangulation, for plane quadrangulation, had accumulation points, and then he showed properties on the accumulation points. We can actually do the same here, and this is something I did before. I first showed that this sequence here had accumulation points, and that each accumulation point of this sequence satisfied some properties. And the properties I showed is that the Hausdorff dimension is 4, exactly as for the Brownian sphere, and the topology is that of the disk. So now I have a metric space with a topological space with a boundary, and we can also show that the Hausdorff dimension of the boundary is 2. So now that we know that this sequence actually converges to 1 and only one limit, we know that this limit satisfies the same properties. So it is a disk, a topological disk. This is why we call this the Brownian disk. And the Hausdorff dimension is 4 for the object and 2 for the boundary. Another picture. So here I have 40,000 faces and a boundary of length 1,000. So the boundary is the red thing here. You can see different colors because you can actually see inside. So you should see that as a somehow half a sphere. So the surface is so the light purple is the inside, and the black is the outside. If you want other pictures, you can go to my webpage and you can actually see them in 3D with a 3D model. You can move them around and zoom in, zoom out, do whatever you want with them. You can also print them out if you have a printer that can do that. What I said so far is when the length of the boundary is of order the square root of n. And we can also say what happens when the length of the boundary is either smaller than square root of n or too big with respect to square root of n. So if the length of the boundary is a little o of square root of n, then the scaling limit is the Brownian map. And if ln divided by root 2n converges to plus infinity, then here, what it means here, it means that you don't see the boundary at the limit. So this is exactly as if ln was equal to 4 all along. And here, if ln is too large with respect to square root of 2n, then you only see the boundary. And in this case, if you rescale as before by this factor, so roughly n to the minus 1/4, then your object is not compact anymore because the boundary is too large. It takes over. So you should rescale with respect to this factor. So if ln is of order square root, if ln is of order the square root of n, ln to the minus a half is n to the minus 1/4. But if ln is larger, this is a bit smaller. And in this case, as you multiply by something that is smaller than before, all the faces disappear. And what you see is only the boundary of your map. So the limit is the same as if you had somehow no area inside your map, only the boundary. And in this case, you find as limit the Brownian continuum random tree, which is the scaling limit of all natural models of random trees. So if you take, for instance, a binary tree with n edges, you rescale it properly, it will converge to the Brownian continuum random tree. And here you observe the same limit. In 2009, Gucci and Guiter also studied the quadrangulation with the boundary and also observed that you had these three different regimes to consider. I will not enter into the details here. So here is another picture. I have 10,000 faces and a large boundary, 2,000. And if you look at it, then, well, from far away, you kind of see a tree. The faces, you have faces everywhere, but they don't take a lot of space because the boundary is too large. And in the limit, you will have exactly the same limit as if you had only the boundary without any faces at all. Now, how about the universality? As before, if you take another class of random maps with a boundary, you have the same limit. And this is something we showed with Gregory. We have actually many results of universality. Let me give you two. The smallest, the easiest one to understand, to define. If you take a 2p angulation, which means that now all your faces have degree 2p instead of 4. So when p is equal to 2, you have quadrangulations. So now you take a uniform map with n faces, still a perimeter of order of length 2ln, where ln is up to some coefficient here that was 2 before, but the square root of n. Then you you need to change the factor here, the red factor here. But when you rescale by n to the -1/4, you have convergence to the Brownian disk of parameter n. So if you take a uniform quadrangulation with n faces or a uniform quadrangulation, hexangulation, so all the faces of degree 6 with n faces, you have the same limit. And this one is also nice and easy to state. You take a uniform map with n edges and parameter 2 ln. So now the faces can have the degree they want, but you have n edges and you have a parameter 2 ln. So the external face has degree 2 ln, and the inner faces, they can have the degree they want. You have convergence to the Brownian disk, the same Brownian disk. Okay, right. We have other results for Boltzmann maps, but I'm not going to go into the details at this point. So these are a lot of results, and the question is, how do we prove these results? So let me give you the main tools to actually understand how these metric spaces work. Maybe the main tool in this area is an encoding bijection, because you know that when you do math, what you really know how to work with is functions that are defined from R to R, or roughly, or Rn to Rn. But here you have a graph, metric space. It's not clear how to encode these in order to show results. So the first step is to encode a map by a simpler object, which is roughly a tree. Here, in the case of the disk, it's going to be a forest. So a forest is a set of trees. I draw them here like this, but this really is a tree. So you can also say that a tree is a map with only one face. So here you have a tree. It's with the drawing is a bit weird, but you will see why. Here you have another tree. Okay, so if I go the right way, here I have the first tree, a second tree, a third tree like this, a fourth tree which is just a vertex, another tree, and a final tree which is just a vertex here. And in the picture, I also link all the roots of the trees with these brown edges. And as you already observed, the vertices of the trees, they all have labels, integers that are on the vertices. And maybe you notice that the minimum label is 1. And you also have other conditions that are a bit harder to say, but to see. If you take an edge, say for instance this one, and you look at the labels before and of the two extremities of the edge, they are either the same like this, or they differ by exactly 1. So here you have the same, and here they differ by 1. And when you go around, you have another rule, which I will not explain here. But the labels, they cannot do whatever they want. So if you have a forest like this with labels on the vertices, you do the following construction. If it's the first time you see it, it's going to be a bit weird, but it will actually give you a quadrangulation with a boundary. So it works like this. So first of all, you add inside the face a new vertex, and you put label 0 on it. Remember that the minimum was 1, so now you have a 0. And you go around the face of your map here. So you go along each trees one by one. And when you do that, you see corners. And these are the corners that are incident to the vertices. So for instance, I go here, I see a corner incident to this vertex here. when I go around, I will see another corner incident to this vertex and so on. So the vertices will be encountered many times when I go along the trees like this. Exactly, I will see a vertex n times if it is of degree n. So I start, let's say, by this corner, and I move along, and I will add new edges, which I will draw from the corner I'm visiting to the following one with label strictly smaller, which means the same label -1. So here I start with the label 3. So I go look for the next two here. Then I keep moving. I'm at the 2 here. And I look for the next one, which is that's here, 3, 2, 1. So it's here. So I link this to this. And I keep moving. So I was at this corner. I go to this corner. Here I'm at label 3. I look for label 2, and it's right there. I keep moving. I'm at label 2. I look for label 1, which is right there. And here, when I reach vertex with label 1, remember that it was the minimum. So I will link it to the extra vertex with label 0. And I keep going. I encounter 2 here. So I look for 1. It's this one. And so on. 3 to 2, 2 to this one, this 3 to this 2, 2 to this one, the 1 to the 0, and so on. And yes, here, when sometimes here I'm at the 2, so I look for 1, I finished my tree, it's not a problem, I go to the next tree to get to the 1, here the 3 to the 2, and so on. And I do this until the last corner of the tour, when I come back to where I started. Now that I've done that, I remove all the original vertices, edges, and you can see that now I have a quadrangulation with a boundary. Well, if you have never seen that, I guess it's not obvious that I'm doing like this a quadrangulation. And neither is it obvious that it's a bijection, meaning that from this, I can recover the object I started with. But it's actually not very complicated to show, but you have to check everything, a lot of things. Everything is checkable, but actually in this area, the harder thing to do is not to show that you have a bijection, but to find the bijection. Okay, some key facts about this bijection. First of all, the number of edges of the forest is equal to the number of squares, the number of quadrangles in your quadrangulation, and the number of trees is half the boundary length. And there is a technical condition that I don't want to talk about. And finally, very, very important, the labels of the forest are the distances in the map to the vertex 0. Well, why is that so? This you can see actually. Of course, the vertex with label 0 is at distance 0 from itself. That's easy. But if you have a vertex with label 2 here, remember that you linked it to the next one. And then when you are at the vertex label 1, you linked it to the 0. So when you do that, you make up a sequence of edges of length where the labels decrease by exactly 1 at each time. So it gives you a path of the right length. And it's actually the best you can do, because when you, as you always link a label L to a L -1, the labels, they decrease by at most 1 when you move along the edges. So they either increase by 1 or decrease by 1. So this is the best you can do. So the distance, the labels on the encoding object are the distances to this guy. So now you have a simpler object, a forest, which is way simpler than quadrangulation. And you have labels, and the labels give you an information about the metric of the map, because they give you the distances to one point. They don't give you all the distances. For instance, the distance between this guy and that guy, I don't know if I just have the encoding object. But the distance between that guy and this one, if I just have the encoding object, I know it's 3. So it has some information, but you don't have all information. Now, let me do the same construction, but 3 by 3. Remember when I was doing my my construction, I moved along the trees, and I told you that sometimes, I think this was the first, this was the first when it arrived. Sometimes the next vertex, the next corner with labels strictly smaller is not inside the tree. And I said, okay, I will link it to, I will look for it in the next tree or the next trees. Now I don't do that. So instead I put a chain like this, telling me that I don't cross it now. And I do the same construction. So here, the same. But now my 2, instead of being linked to this one here, it is linked to the point of the chain with the right label. So on my chain, I started at the end of the tree, and I started with label 3. So I put a chain of with label 2, 1, 0. And I do the same with the next tree. So here I have a 2. So I will put a 1, 0, and I do my construction. And here I do the same. Actually, as my minimum label of this tree is 3, it means that I just need a 2 as minimum. I don't need to have here 1 and a 0, because I will never link 4 or 3 to a 1 or a 0. And I do the same construction and so on. So now I have, if I had L trees, now instead of having one map, I have L maps, but these are pieces of the original map. Because what is the difference? So I put these green chains here, and I said instead of looking this 2 to this one here, I link it to this one here. So if I glue this one with this one, I get the same thing. And the same goes for here. Instead of linking this one to the 0, that's what the same 0 for everybody, I put a 0 for it for this one. So if I glue the red path with the green path, I recover the original disk. So these are called slices. So these are parts of the disk that correspond to actually the trees of the encoding forest. So here is a picture. It's the same picture as before, but I use a different color for each slice. So you can see that some slices are small, and here is a big red slice, and so on. What is the time? Okay. So now I have encoded my maps with roughly forest or trees with labels. And now I want to see how it works. So let's start with the Brownian map. So the Brownian map is when I only have one tree. This is why I could, L was the number of trees. I only have one tree. So if you take a uniformly chosen quadrangulation with n faces, then you take a uniformly chosen vertex in it. Then like this, you get a quadrangulation with a given point. And you can do the bijection, because maybe I forgot to say that. But in the bijection, we have, actually, this gives you a bijection between, label forest and pointed quadrangulation. a pointed quadrangulation is a quadrangulation given with one point, and this is the point in question. And you have the distances to this point. So if you take a uniform quadrangulation, which was the problem we wanted to, we started with, then you take a uniform vertex inside your quadrangulation. You have a quadrangulation now that is pointed. You can encode it by one tree with labels. Let's forget about the fact that the labels are positive in the encoding object, with the minimum being 0. You translate them, and then you see that this tree, it's a tree, it's a uniform tree, so it converges to the Brownian CRT, which I told you was the universal scaling limit for trees. And the labels on the tree, they converge to a Brownian motion indexed by the tree. Remember that the labels on the trees, they satisfy the constraint that the labels of two vertices linked by an edge, they were either the same or they differ by 1. So this gives you a random walk. So if you take a branch of a tree, this gives you a random walk, and it converges to the Brownian motion. But instead of having a Brownian motion indexed by R or R2, you have a Brownian motion indexed by a tree. So on each branch, you have a Brownian motion, and whenever you have a branching point, you start 2 independent Brownian motions. So it looks like this. So you have a tree, and on top of it, you have Brownian labels. So let's say that this is the point 0. You put Brownian motion here, and there, when you have a branching point, you start 2 different independent Brownian motions. And then you do the continuum equivalent of the bijection I told you. What was the bijection? I was doing the tour of my tree, and whenever I had a point with label L, I was looking for the next one in the tree with label L-1. Now I'm at the limit of that, so everything has been rescaled. So the -1 goes to, once rescaled by n to the -1/4, it goes to 0. So the condition becomes that I should link a point with the next point with the same label. So it means that the label of this guy is the same as the label of this guy. And in between, all the labels are larger. And in the end, putting an edge of length 1, once we scale, it goes to an edge of length 0, if you want. So it means that I identify these 2 points. So in the end, I have a quotient. So these two guys, they are identified if they have the same label, and on the green, on the red piece here, everything is larger. It can be either A to B or B to A. Maybe the edge goes the other way. So, but on one of the 2 sets, all the labels are larger. So you identify these, and this gives you a metric space, which is the Brownian map. I don't know how much time I have. Okay. What is the construction for a slice? Now you do exactly the same construction. So you have your Brownian tree with Brownian labels, but now you identify A to B only if they have the same label and all the labels from A to B are larger. When I did the construction, I said I link like this, but if I need to go to the next tree, I don't do it. Remember, I put this green chain of edges telling me that I cannot go to the other tree, to another tree. So this means that now I cannot go from B to A, even if the labels in between are larger. when I do that, I have, instead of having the Brownian map, I have the limit of a slice. And from the knowledge of the Brownian map, of the convergence to the Brownian map, I have a convergence of the slice. And once I know that all the slices converge to objects that I know, which can actually be constructed from the Brownian map, then I can show the convergence of the Brownian disk. So let me just skip that. So the thing goes like this. On the brown, remember the brown circle I had before, which corresponds to the boundary of the disk. I have the labels. I did not tell you what they were satisfying, but in the limits, the good news is that it's Brownian motion. So you have a Brownian motion on this, and you put Brownian slices. So the limits of the slices, they don't all have the same size. Some are smaller, some are larger, but you put them like this, and then you just have to glue them together. So by this blue thing here, I mean that I will identify the points like this. So I will reglue them together exactly as I did on the picture, on the discrete picture, when I told you that from the slices, I can recover the whole map. So just to recap, I have an encoding of a Brownian disk by a forest. For each tree of the forest, it gives me a slice. And if I glue the slice together, I have the disk. I take the limit of the slices, and then I glue back the limits together to get the limit of the whole thing. There's just one problem, that when I do that, I have an infinite number of slices. But the good news is that the good news is that when I take a geodesic between 2 points in the disk, it only crosses a finite number of slices. So what it means is that the small slices, they exist, but they are all close to the boundary. So if I go at distance, say epsilon from the boundary, I only see a finite number of slices. Each of them converge to something that I understand, some version of the Brownian map. So I can glue this finite number of pieces together and have something that I can work with. So that's the rough idea of how we show convergence either to the Brownian map or Brownian disk. Okay, and so this. Thank you.
Thank you very much. This was an excellent talk, and we're always very proud that our students make a lot of questions. So let's see if this is the case. Who wants to start? Maybe I start with a bad question. So you presented basically two ways of representing these maps. One handmade, and I think I understand this one quite well. And then you show computer-made pictures, which look very impressive. But I'm not sure how to interpret them and how to put these two pictures together, basically.
This one, maybe?
Yeah, for example, what does it mean, the peaks?
Oh,
and
all the pictures, you mean? Well, yeah. It means, okay, it means that okay, maybe I didn't say exactly what the computer does. The computer puts all the vertices in R3 in such a way that the length of the edges should be roughly the same, as best as possible, and the vertices. Okay, so it means that somehow you have the edges behave like a spring. Okay, so they are supposed to have all the same lengths, one, and so if you extend them, so you have an edge. You see it as a set of points with physical constraints. So you have an attraction of the points if there is an edge, like a spring, and you have an electrical repulsion between points. Otherwise, everything will be on the same, everything will be at the same place. And so having a spike like this, it means that you have a lot of faces. Well, I don't really know what. Okay, the thing has dimension 4, so it means that it should take. It's not big, but it takes a lot of space. See what I mean? The diameter is n to the minus n to the 1/4, and it has n. So it has n faces and diameter n to the 1/4. So you need to I don't know, to put things in like fold it a lot. It's kind of the Brownian motion, you know. It's homomorphic to a line. If you take the graph of a Brownian motion, of a one-dimensional Brownian motion, but it has dimension 3/2. Okay, so it's really folded on each other. I don't know how to say that. I don't know if I answered your question, but
you did. So is it fair to say that these peaks and spiky places are where you see more density of points? This is
yeah. Well, the points, they're all they're actually, there's not a lot of points in this bulk here. Everything is in the spikes. Yes,
right.
That's right. And for the CRT, all the points are actually leaves. Okay, so say it's a tree. My picture was very, very bad. This picture here, actually the dimension of the leaves, so the points of degree 1 here, it's 2. And the dimension of the points that are not leaves is 1. Okay, so all the points in, if you take points uniformly at random in the Brownian tree, it's a leaf. So it's kind of the same property that you said. That's exactly right.
Yeah. So who would like to make a question? Sandra?
So I have 2 questions, maybe. One is related with what Adrian asked. So in your last slide, you showed us that one. So you say that if you have a positive distance, then you have a finite number of that lines. So that is related with the other picture that you show, that maybe from the center you have like a lot of
okay, so what it means? It means that although, as we said, all the points are in the spikes, but when you want to go to this point to that point, after a time epsilon, you actually only go through the bulk.
Yeah.
Because actually, yes, as all the points are in the spikes, if you want to go to a point to another one, you should avoid the spikes if you want to go fast.
Yes.
So the geodesics, they are far from the spikes.
Because I was wondering, like they look like large lines, and then maybe you have something big. If you can count how many of that have. So if you define as a length, then that they are related with the other picture that you showed us.
Which one?
Yes. So in the picture, it looks like you have a big center thing, and then you have like a lot of spikes. So if I want to know how many spikes I have with some size, that is related with the other picture that you show us, that they have like.
Actually, I'm not this one. Okay.
No, the
last one.
The last one, yes.
Yeah. Okay. So actually,
that one.
The spikes are everywhere, right? what I said here is that when you go to from a point to another point, you avoid the boundary, but you also avoid the spikes. So this is actually two different things. Maybe I was not really clear about that. What is really important is that so maybe this on this picture here, if you want to go from a point to a slice to another, so okay, here you don't have a lot of slices. You go far from the boundary, so you only the small slices are all along the boundary.
Mm-hmm.
Inside, you only have a finite number of slices. And another key property that I use is that I actually know all the geodesics to a given point in the Brownian map, in the Brownian disk. And if I take 2 points inside the disk, then the geodesics, there is actually, if I take 2 uniform points in the disk, there is one geodesic, and I know that it does not touch the boundary. So it stays far from the boundary. Okay. But the spike things I said it's more of an intuition that I don't really have I don't have any results about that. I don't really know how to define something actually a notion of spike or stuff like that. This is just an intuition, not really. I think a nice thing I can say is actually if I take 2 points, I see 3 points inside the Brownian disk, and I look at the geodesics. Can I draw on it? How do I draw on it? Maybe. What should I say? This maybe? Okay. If I take 3 points uniformly at random in the Brownian surface, which the Brownian sphere, Brownian disk, whatever, and so I will have one geodesic like this, and actually I will have a unique geodesic from this point to this point. And if I now take a third point and I look at the geodesic between this point and the one on the bottom, then it will look like this. And there, after a while, they are the same geodesic. So the intuition I have behind this is that if I take this point is a point somewhere in one spike, and these are points from other spikes. So if you want to go from this spike to this spike, somehow you need to go through a bottleneck. And then once you are there, you only have one way to go to this point. So that's a very nice property, which is called the confluence of geodesics. And it works for every Brownian surface.
Thank you. I have another question. I don't know if you can go back to your slides, please.
Yes.
So if you go to the last one from the Brownian disk, you gave us yes. So if the Ln is something or it has the same convergence as L square root of p minus 1n goes to the you have that limit. But what happens if it goes bigger? Can you say that it goes to a random tree?
Yes.
Yeah. And it's the same random. It is the same random tree.
Yes. Yeah. Yeah. The result I said for about these results, I only showed them for quadrangulations, but they also hold for other maps for which whenever I can whatever I can say. I'm not sure I don't think we did it in the paper, but everything we can say here, we can also say the same thing when ln is either ln divided by this either tends to 0 or to +infinity. Everything will work the same.
Do you have more questions?
Hi. Well, I have a
Yes.
question. Thank you for your talk. It's really nice. Yeah. But I have a question about well, which is the problem when you if you can consider non-orientable surface.
Mm-hmm. What is the problem with that? With that, the problem is the bijections. Well, it used to be here I showed you a bijection, which is the easiest one for. Well, the easiest one is for just the sphere. For the disk is a bit more complicated because now you have instead of having just one tree, you have L trees, but you can actually generalize these bijections to other surfaces. You can do it for compact surfaces with a boundary, so genus G and holes, and you can actually generalize it to non-orientable surfaces. But this is a very recent result, and so far we haven't shown, we haven't studied non-orientable Brownian surfaces, but it's something that I plan to do, and everything should work.
Yeah.
Many details because the bijection become a bit messy with the non-orientable surface.
Yeah, yeah.
But it works.
Thanks.
It exists.
Yeah, thanks.
Actually, the paper on Brownian surfaces, we are finishing it with Gregory. So the paper about Brownian disk is called the Brownian surface 1. There is a Brownian surface 2 that should come up soon, very soon, and it focuses on the compact orientable surfaces.
Yeah, thank you.
Thank you.
Thank you. Are there more questions or comments?
I have one really basic question.
Yes.
Maybe I should have asked it at the beginning. I don't really understand why we define phases the way we define it.
Wait, faces?
Yeah, phases like a map phase. Why do we consider the complement?
It just means that you if you remove the graph, then what is left is the faces. That's just a definition. How would you want to define them? I mean, it's just an area delimited by the edges. So it's by the complement, I mean the complement of the edges. That means that if I take the sphere minus the edges, then I get some topological disk, and these are the faces.
Okay, yeah, because I was trying to make the connection with real, geographical maps. So
yeah, so if you take a geographical map and you remove the boundaries, the borders, yeah, it's called a border. You remove the borders and you're left with countries, right? And the countries are the faces, or the lakes and seas.
okay, thanks.
Are there more questions? If not, well, thank you very much, Jeremy, for
Thank you very much.
Nice talk. I think we enjoyed it a lot.
Nice, thank you.
Thank you.
Thank you very much, and see you sometime.